The chapter's root, what independence of errors meant, what clustered data does to it, multi-level models as one response, panel data and fixed effects as another, then presentation conventions and the code in both languages. Your goals: explain when errors become dependent, understand what ignoring within cluster dependence does to standard errors, apply cluster-robust inference in R and Python, choose between clustered least squares and multi-level models, recognize panel structure, run the within estimator, and present fixed effects tables properly. Recall the two error assumptions behind our inference: constant variance and independence across observations. The sandwich estimator already freed us from the first. This chapter relaxes the second, and the division of consequences on this page organizes everything ahead. With dependent errors, the coefficient estimates remain unbiased and consistent, but the standard errors are wrong, typically too small, so tests and intervals mislead. Where does dependence come from? 4 recurring structures: clustered data, where units share classes, hospitals, firms or villages, and hence common unobservables. Panel data, the same unit observed repeatedly, its unobserved character persisting. Spatial data, where neighbours share geography and climate, and hierarchies, students within classes within schools. The key question at the bottom will drive every decision. Does the variable of interest vary at the group level or within groups? Project Star makes the problem concrete. Class size was randomized at the class level, so the regressor varies only across classes, never within one, while test scores vary by student. Students in the same class share a teacher, a room, and peers, so their errors are positively correlated. Least squares, treating every student as independent evidence, understates uncertainty, and the t-statistics come out too large. Decompose the error and the mechanism is transparent. Each student's error is a cluster-level shock, the same for everyone in the class, think teacher quality, plus an idiosyncratic piece. Units in the same cluster correlate precisely because they share the common shock. And whenever cluster-level variables are omitted from the model, that shock sits in the residual. The standard remedy is the cluster-robust variance estimator, the cluster sandwich. It allows arbitrary correlation of errors within each cluster, assumes independence across clusters, and needs many of them, a rule of thumb of 20 to 50 groups. Note what does not change. The least squares point estimates are untouched. Only the uncertainty attached to them is corrected. The star comparison shows the hierarchy in action for the reading score regression. Ordinary standard errors, assuming independence. Smallest, with the largest t. Heteroscedasticity robust, slightly larger. Cluster robust by class, the largest standard error and the smallest t, and for this design, the correct one. Same point estimate in every row, only the honesty of the uncertainty differs. When does clustering actually matter? 2 conditions together. The key variable varies at the group level, like class size, and residuals correlate within groups. It matters little when the key variable varies purely at the individual level, like birth month, with no group-level confound. The practical rule to memorize: always cluster at the level of the key treatment or variable, or higher. Why exactly are the ordinary standard errors wrong? Because the formula counts the students in a class as that many independent pieces of evidence about the class size effect. Sharing the same teacher and room, they carry far fewer than that many independent observations. The cluster-robust estimator fixes the accounting by summing contributions within each cluster before squaring. How large is the understatement? The design effect: 1 plus cluster size minus 1 times the intra-class correlation. With a correlation of 0.15 and classes of 20, that is 3.85, so the ordinary standard error is too small by its square root, roughly a factor of 2. Reported t-statistics can easily be double what they should be, and significance based on them over-rejects. The decision rule for where to cluster, at the level where the key variable is assigned or varies. Class size randomized by class. Cluster by class. Policy varying by municipality, workers in firms, by firm, individual treatment varying by birth month, no clustering needed, and when uncertain, the page advises the higher, more aggregated level, which typically yields larger, more conservative standard errors. 2 refinements. Do not cluster reflexively. If treatment truly varies at the individual level with no omitted group-level confound, overclustering just inflates standard errors unnecessarily. And two-way clustering, by entity and by time together, suits panel data, where errors may correlate both within units over time and across units within the same period. What if there are few clusters, fewer than 20? The cluster-robust estimator is an asymptotic device, and with few groups it becomes unreliable. The options: fall back on ordinary standard errors and acknowledge the limitation. Use the wild cluster bootstrap beyond this course, or model the cluster structure explicitly with a multi-level model. Below 10 clusters, extreme caution. Multi-level models are the explicit modeling alternative. Instead of correcting standard errors after the fact, write down the error structure. The random intercept model gives each cluster its own intercept, drawn from a normal distribution with its own variance, and estimation proceeds by generalized least squares or maximum likelihood rather than ordinary least squares. The trade is stated crisply. If the variance structure is correctly specified, multi-level estimates are more efficient, with smaller standard errors, and the model decomposes variance into between-cluster and within-cluster parts, often interesting in itself. The price? It requires that specification to be right, and if it is wrong, the inference can mislead. Hierarchies extend the idea naturally. Students within classes within schools give a 3-level model with a school-level shock, a class-level shock, and student noise, each carrying its own variance component estimated alongside the regression slopes. The algebra grows another layer, but the logic is unchanged, the same decomposition of the error applied twice instead of once. So which tool when? The table's advice. For slopes on group-level variables, least squares with cluster-robust standard errors. For variance components, a multi-level model. For predictions within groups, multi-level often wins by avoiding overfitting. For slopes on individual level variables, least squares with entity fixed effects and robust or clustered standard errors. The key message: choose by the research question, not by habit. Panel data observes n units at multiple time points, balanced if every unit appears in every period, unbalanced otherwise. The examples set the scale: 1,000 individuals over 10 years, the Swedish municipalities every 4th year across 2 decades, 50 countries quarterly. And the connection to everything so far: each unit is its own cluster, errors correlated within units over time. The panel error structure has 3 parts: a unit fixed effect, the time constant unobserved character of each unit; a time fixed effect, the common shock hitting all units in a period; and idiosyncratic noise. One notational distinction to hold: some variables vary only across units, while others vary across units and over time, and only the latter survive what comes next. Now the running example. 290 municipalities over 6 elections, tax rate as outcome, a left coalition indicator as regressor. Naive least squares, ignoring the panel structure entirely, gives a coefficient of 0.682 with a standard error of 0.059. But tax rates are persistent within municipalities, so errors are correlated within them, and that standard error is too small. Clustering by municipality corrects it. The same coefficient, Now, with a standard error of 0.091, about 54% larger, clear evidence of within-municipality correlation. The interval runs from half a point to nearly 9/10. Adding year dummies, time-fixed effects moves the coefficient to 0.769 and tightens the clustered standard error. Common year shocks were both noise and mild confounding. The within estimator goes further. Subtract each unit's time average from every variable. The unit effect, and every time constant characteristic with it, cancels out exactly. It is equivalent to a dummy for every unit without estimating them explicitly, and it uses only variation within units over time. The advantage deserves italics. It controls for all time constant unobservables, including things no one can measure. Apply it to the municipalities, and the story turns. With municipality fixed effects alone, the coefficient collapses to minus 0.013, indistinguishable from zero. With municipality and year effects together, it is 0.096 with a clustered standard error of 0.028. Compare the pooled 0.682. Most of the raw correlation reflected systematic differences between municipalities, not the political regime. The control chart. Entity fixed effects absorb all time invariant unit characteristics, geography, culture, initial conditions. Time fixed effects absorb common shocks, business cycles, national policy. County by year effects absorb regional shocks that vary over time. And the built-in limitation. Fixed effects cannot estimate the effect of anything that does not vary within units. Here is the full 5-column table. Cluster robust standard errors by municipality throughout 1,733 observations. Pooled 0.682, year effects 0.769, municipality effects minus 0.013, two-way 0.096, county by year added 0.089. The caption draws the lesson. The raw correlation collapses once municipality effects enter, the signature of omitted variable bias in the pooled estimates. Missing data deserves one page of care. If observations are missing at random, unrelated to the outcome, unbalanced panels are fine, and the same holds when missingness relates only to variables in the model. The danger is missingness related to the outcome itself. Patients dropping out as health deteriorates, then results may be biased and no clustering correction fixes it. Presentation conventions. Never list hundreds of fixed effect dummies. They are nuisance parameters. Show only the coefficients of interest. Mark included fixed effects with check marks. Always report the sample size and the clustering level. And show multiple specifications side by side, pooled, year effects, entity effects, two-way, so readers see the progression. And state the clustering explicitly in the table note. The R code for clustering walks the star data through the 3 levels of the hierarchy: ordinary standard errors, heteroscedasticity robust, and cluster robust by class through the clustered covariance function. 3 calls, 1 fitted model, and the comparison from the earlier table reproduces itself on your screen. The multi-level alternative in R is the mixed model package, a random intercept by class, written in one formula with the group syntax in parentheses. The summary returns the fixed effect coefficient for small classes alongside the class level and residual variances, and the ratio of those two variances is the intra-class correlation, the quantity that drove the design effect earlier. For the municipal panel in R, read the data, drop Gotland, whose tax structure is not comparable with the rest, then fit pooled least squares with municipality clustered standard errors, and finally add year fixed effects through the factor function. 2 models, 1 line each, and each carrying honestly clustered uncertainty rather than the naive default. The within estimator lives in the panel package. Declare the index as municipality and year. Request individual effects and cluster the covariance by group. The demeaning, the dummy bookkeeping, and the degrees of freedom are all handled internally. Your job is the specification, not the arithmetic. Two-way fixed effects change exactly one argument. The effect option becomes two ways, so the estimator absorbs both municipality and year effects at once. The clustered covariance call is unchanged from the previous page. This single line is the specification behind the fourth column of the results table, the estimate of about 0.096. The Python preparation for STAR shows honest data handling. Build the small class indicator explicitly. Treat the aid classes as regular. Drop incomplete rows on exactly the variables in use, then fit by the formula interface. The care in constructing the indicator is not pedantry. A silent coding slip here poisons every later number. Python's 3 standard error levels mirror ours exactly: the ordinary summary table, the heterosedasticity robust request, and the cluster robust version with the group's argument set to the class identifier. One fitted model, 3 covariance choices, and the same lesson repeats about which of the 3 is honest under class-level assignment. The multi-level model in Python is the mixed linear model. The same formula, groups by class, fitted by restricted maximum likelihood. The variance components come back as the group covariance and the residual scale, and one line of arithmetic turns them into the intra-class correlation. Panel fixed effects in Python use the linear models package. Drop Gotland, set a 2-level index of municipality and year, add a constant to the regressor matrix, then fit panel least squares with entity effects and entity clustered covariance. The printed summary reports the within estimate together with its properly clustered standard error. Two-way fixed effects add a single argument, time effect set to true, while keeping the entity clustered covariance from the previous page. Entity and time both absorbed, uncertainty clustered by municipality. This is the exact Python twin of the fourth column in the results table, and the numbers agree with the R output. The mid-chapter summary in 4 lines. Least squares stays unbiased under dependent errors, but its standard errors are wrong. Clustered data calls for cluster robust standard errors with at least 20 to 50 groups. Multi-level models buy efficiency and variance decomposition at the price of specification risk. And panel data is clustering by another name. Each unit is its own cluster. Fixed effects. In summary, time effects remove common shocks. Entity effects remove all time constant unit differences, observed or not. Two-way effects control both, at the price that only time-varying variables remain estimable, and report it all in a table with effect indicators and an explicit clustering level. 5 discussion questions. The fourth has teeth. 15 countries over 20 years. The key variable varying only across countries. Can you include country fixed effects at all? And can you honestly cluster by country with 15 clusters? The intra-class correlation gets its formal page. The cluster variance share of total variance. 0 means clustering is irrelevant. 1 means all variation is between groups. Education data typically sits between 0.1 and 0.25 at the class level, and the closing advice is practical. Compute it before deciding whether clustering matters. The design effect turns the correlation into a multiplier. 1 plus average cluster size minus 1 times the intra-class correlation. The worked case, correlation 0.15, classes of 20, design effect 3.85, effective sample size, the nominal count divided by nearly 4, ordinary standard errors too small by a factor of 2. Cluster robust standard errors absorb all of this automatically. Time-fixed effects, why and how, outcomes trend and share common shocks, inflation, recessions, policy changes, and time dummies absorb anything common to all units in a period, observable or not. Implementation is one gesture in each language. The factor function in R, the time effects flag in Python. What remains afterwards is within period cross-unit variation, entity fixed effects, the intuition once more. Municipalities with historically left-leaning electorates may also have high tax traditions, confounding ideology with culture. Entity effects subtract each municipality's long-run average, leaving only its changes over time. The demeaning interpretation is exact. Regress deviations from unit means on deviations from unit means. The within estimator's own assumption is strict exogeneity. The error at any time must be mean independent of the regressors at every time, given the unit effect. That rules out feedback, past outcomes driving future regressors, and anticipation, future policy shaping current outcomes. The practical check. Could future values of the regressor plausibly relate to current outcomes? If yes, the within estimator is biased, and dynamic panel methods lie beyond this course. Choosing the clustering level, consolidated. Cluster where the key variable is assigned or varies. The examples repeat by design, class, municipality, firm. When uncertain, the more aggregated level typically gives larger, more conservative standard errors. And two-way clustering, entity plus time, covers correlation across units within a period and across periods within a unit. One formula argument in R, fixed versus random effects in one table. Fixed effects treat the unit effect as a parameter, one per unit, and stay consistent even when it correlates with the regressors. Random effects treat it as a draw from a distribution, gain efficiency, and go wrong exactly when that correlation exists. The entire choice turns on one question: is the unit effect correlated with X? The Hausman test asks the data that question by comparing the two estimates. A significant difference says the random effects assumption fails. Use fixed effects. An insignificant one permits the more efficient random effects. And the page's last line is the practitioner's consensus. With observational data, fixed effects is almost always the preferred choice. Before estimating any panel model, run the diagnostics. How many observations per unit, and how is that distributed? Is missingness random or systematic? Are there structural breaks, mergers, boundary changes? R has one-line answers for each. And note why Gotland leaves the municipal data. Its tax structure is non-comparable, a substantive reason, not an imbalance problem. The presentation template in miniature, 5 columns from pooled to county by year, the key coefficient marching from 0.68 to 0.09, check marks tracking which effects enter, clustered standard errors, and the sample size throughout. The caption states the philosophy. The story is in the pattern across specifications, not in any single column. The formula card for dependent errors, the cluster decomposition, the intra-class correlation, the design effect, the panel decomposition with unit and time effects, the within estimator as demeaned regression, and the cluster robust standard error, consistent as clusters grow, wanting at least 20. 6 lines that summarize the machinery. 3 exercises. Municipality clustered standard errors on the test score data, explained through regression anatomy, the pooled, year effects, and municipality effects progression tabulated and interpreted, and the within estimator computed by hand through demeaning, checked against the panel package. 2 more, adding county by year effects and naming the confounds that addresses, and the discussion with teeth, whether the within estimator gives a causal effect of ideology on taxes when tax rates partly determine future political outcomes. The standard error hierarchy, 1 row per situation, ordinary, rarely justified, heterosadasticity robust for cross-sections without grouping, cluster robust for grouped data with enough clusters, two-way clustering for panels, and hack or Nui West for time series with serially correlated errors, the tool introduced in Chapter 12. The closing principle: when in doubt, the more conservative option. Wide, honest intervals beat narrow, wrong ones. Two-way clustering in R is written as a formula inside the covariance call, cluster by municipality plus year, then compare it directly against the one-way municipality version below it. 2 lines of code, and the comparison between the two sets of standard errors itself tells you whether cross-unit correlation within periods actually matters for these data. The Python setup for the same exercise: read the municipal file, drop Gotland, set the municipality and year index, and add the constant to the regressor matrix. Nothing statistical happens on this page at all. It is the disciplined bookkeeping that makes the estimation call on the next page trustworthy rather than accidental. And now the estimation call itself. Panel least squares with both entity effects and time effects, with the covariance clustered by entity. Printing the summary and the parameters gives the two-way fixed effects estimate together with its clustered uncertainty, and the numbers match the R result from earlier in the chapter to the digit. The identification page is the deepest in the chapter. Pooled least squares blends between unit and within unit variation. The between estimator uses group means only. The within estimator uses only changes inside each unit. For the municipalities, between variation is confounded by tradition, and the collapse from 0.682 pooled to about 0.096 within measures exactly how much confounding the between variation carried. The panel estimator table closes the loop. Pooled uses everything and controls nothing. Random effects weights both sources and assumes the unit effect uncorrelated with regressors. Within and first difference both purge all time constant effects. Between uses group means alone. For most observational panels, the standard is the bottom line, the within estimator with cluster robust standard errors. A reference card for the R mixed model package, how to install it, the random intercept formula with its group syntax in parentheses, the restricted maximum likelihood default and when to switch it off for likelihood ratio tests, and the extractor for variance components. Keep this page for the day. A variance decomposition is genuinely the research question. And its Python counterpart on the final page, the mixed linear model with its groups argument, the variance components recovered from the group covariance and the residual scale, and the intra-class correlation obtained in a single division. With that, both languages now cover every method this chapter has promised.